Hello, welcome to the course on audio signal processing for music applications. This week we introduce the concept of stochastic signals and a way to model these type of signals using spectral approximation. So in this demonstration class, I want to actually use an implementation of this model of the SMS tools package and see how it works. So let's open the interface of the SMS tools, and let's first use the short time Fourier transform to try to understand the sound. So let's open a sound. A good sound for stochastic analysis is the ocean sound. Is very noisy, so that would be quite good for this type of approximation. In terms of parameters, the default are okay. Humming window size 124, hop size 512. Well, let's first listen to the sound. And now let's compute the STFT. Okay, so here we see the spectrum of this ocean sound, and clearly is the kinds of things we expected, in the sense that the magnitude spectrum is very granular. I mean, there is very little kind of repetitive structure. The only kind of a structure we can see is this overall shape in which we see basically the amplitude, the swelling of the waves being shown here as this increase of this red area. And also we see that the higher frequencies are softer than the lower frequencies, so there is a much more emphasis on the low frequencies. And in the phase spectrum, we basically see random numbers. There is nothing particular here that we can see in terms of a given structure. And if we zoom into the phase spectrum, definitely it will corroborate this idea that these are basically random numbers. If we do it on the magnitude spectrogram, maybe one of the areas that are more sort of stable, and yeah, it's also very noisy. Of course, in here there is some more overall trends that we can see. But now let's see what we can do with the sinusoidal model that we have been talking about and using. So let's take the sine model. And let's get the oboe sound, the ocean sound. Okay, and in here we definitely will need a lot of sinusoids. In terms of the window size, I don't think it matters too much, but maybe let's take a smaller window, let's say 1,000. Here since the phases do not matter, that we can really just say 1024 and FFT 1024. There is no need for doing anything different from that. The hop size will be 1/4 of that, so that would be fine. Magnitude threshold -80. Well, the duration of the sinusoids here, clearly we need to account for tiny sinusoids that will come in and out. And in terms of the number of sinusoids, well, we need a lot. So let's put 200 Hertz. And this tracking, I don't think this matters much, because they're gonna be coming in and out all the time. So let's see what happens. Okay, so that's quite a lot of sine waves and a quite longer sound, so that may take a little bit longer. Okay, so this is what we get. Again, maybe what we were expecting. The sine waves, these are the frequencies. They are all over. We just see that they are scattered all over, again in a very kind of granular, random way. Let's listen to the sound that is synthesized from this sinusoidal model. It doesn't sound too good. It has this kind of tonal quality, and we hear like pitches that were not really in the original sound. This is why the sinusoidal model may not be that appropriate for this type of sound. We can push it more and make it sound closer to the ocean sound, but clearly it's not an appropriate modeling approach for this sound. So now let's go to the stochastic model, and let's open the ocean sound. Okay, and in here there is not that many parameters to choose. One is the hop size, and the FFT size will basically be twice as that, so there is no need to control that. And then there is an important parameter, which is this smoothing approximation factor, which is basically how much smoothing we're going to perform. For example, we can start by 0.1. That means that we're going to reduce the size of the FFT by 90%. So we're going to have, the result is 10% of the overall. So that means that we're going to have only 1 every 10 beams or frequency samples in the frequency domain. And of course, the phase spectrum will be random numbers. So let's listen. Well, let's compute that. Okay, that's quite fast. And here, of course, what we are seeing, and maybe we can compare it with the original STFT, we have a magnitude spectrum which is much coarse, so there is much fewer horizontal lines because we have the FFT size was downsampled, was basically was smoothed out. Okay, and but let's listen to the output sound. Well, it doesn't sound like the original. Let's listen again the original. But it definitely sounds like some water, so the quality is very much the same. It sounds with a kind of high pass kind of thing. So let's try to get a little better. Let's have a hop size smaller than this one, maybe 64, because these time changes are important. And maybe let's not reduce this that much. Let's 0.5, and let's see what happens. Okay, now we have more information. We have a finer grain both in the horizontal and vertical axis. So let's hear what is the result. Yeah, this sounds a little bit better, and we can play around with these parameters to get different types of approximations. Now, to finish this, let's try how this approximation works with a sound that is not really completely stochastic. So for example, let's open the speech sound. Let's open this speech male sound. Okay, and let's not do so much. Maybe let's do 256, and let's do maybe 0.2 as an approximation. Let's first listen to the sound.
Do you hear me? They don't lie at all.
Okay, so now we're going to attempt to approximate this. We're going to get rid of the phase spectrum. We're going to make it like random numbers, and we're going to smooth out the magnitude spectrogram. So let's see how it sounds. Okay, so this is the approximation. So this was the original sound. This is the stochastic approximation. We see a very coarse type of approximation to the magnitude spectrum. And this is the resynthesized sound. Let's listen to that.
Do you hear me? They don't lie at all.
Okay, that's very interesting. In fact, it sounds like a whisper type of sound. We have lost all the pitch information because a lot of this pitch information is in the phase spectrum, and we have basically got rid of that. And since the magnitude spectrum is quite smooth, also we got rid of quite a bit of the possible pitch information that was present in the magnitude spectrum. Okay, so that's all. That's what I wanted to show. So we have looked at one implementation of this stochastic approximation that we have talked about. Within the SMS tools, we have this code that approximates a sound using this model. And well, we have used some sounds from Freesound. So hopefully that has given you a flavor of what does it mean to approximate a sound with this stochastic modeling approach. And of course, we're going to be using that for the residual of some signals. And so in the next demonstration class, we're going to put it together with the other models that we have been talking about. So we'll see you next class. Bye bye.